Hello friends, welcome back to visit my channel. I'm really happy to see you. Consider me your friend, control philosopher and guide. Okay, so today we will understand problems like harmonics, and finally we will see how to actually configure a VFD for use. Okay, let's get going. See, configuring a VFD for use or installing a VFD is less complicated than what most people think. Basically, you have to install it correctly with proper earthing and all that. And then the most important thing is to have the motor nameplate data readily available with us. Okay, we get going. First, we talk about sizing the VFD for a given motor. The first thing we must consider is the conditions of overload. There is either a low overload duty or a high overload duty. A high overload duty means you can draw up to 150% of motor's rated load current, 1.5 times its normal current, full load current, for about a minute or so. Okay. Whereas in the case of light overload, this means only an increase of 10% over the maximum full load amperes of the motor. Okay. If the conditions of high overload duty are foreseen, then we must select a VFD that is typically one size higher. Okay. You look at the table below on the left side. You see in the first line, for the first VFD listed, that is, ACS 550, 23 ampere, etc. That can be used for a normal use or a light overload duty for a motor of 11 kilowatt, right? But when it comes to a high overload duty, it can be used on a motor of just 7.5 kilowatt. Okay, so if you were to need to operate a 11 kilowatt motor on a high overload duty, that means you'll have to select the next size of VFD, that is the one rated for 31 ampere on the second line. Okay, this is the same VFD that would ordinarily be suited for a 15 kilowatt motor when that 15 kilowatt motor is run at light overload condition. Fine. Additionally, you must consider the effect of ambient temperature. As you can see on the two graphs at the right, up to 40 degrees ambient temperature, you need not derate the VFD. However, after um, um, after a increase of 1 degree over 40 degrees ambient temperature, you must correspondingly derate um, the power rating by 1% for each degree above 40 degrees. You know, okay. So also, because the density of air at higher altitudes is less, its ability to cool will be correspondingly less, which is why we must derate the VFD by 1% of its power rating for every 1000 meters increase in altitude. 1000 meters is about 3000 feet. Okay, it's as simple. Now this consideration of overload and derating for altitude, derating for ambient temperature should be done at the time of selecting the VFD for a certain application. And of course, the main consideration is the VFD should be the same as the power rating of the motor to be controlled. Okay, now we come to the basic principles that must be observed when installing a VFD. See, most VFDs are within electrical control panels, typically MCCs. Sometimes they can also be part of a PLC panel. Although VFDs are quite efficient, they are about 97% energy efficient. They still give out a large amount of heat. They dissipate quite a lot of heat. Means, let us say that if you have got a 10 kilowatt motor, it will easily dissipate in hundreds of watts. Okay, so we must take care of this by providing cooling inside the cabinet. Okay, then you must bear in mind that VFDs also give a high degree of noise and also electromagnetic interference. Okay, now the for cooling, we have to calculate it. The cooling fan to be installed in the MCC cabinet or feeder cabinet or PLC cabinet has to be in line with the heat dissipation of the drive. And this, of course, you have to uh, consider it together with the maximum allowed temperature rise with respect to ambient temperature and all these things. These are all factors that influence the design of the panel or enclosure. Okay. Then we come to the point of grounding. See, grounding or earthing the VFD is very, very important. All VFDs have got solid metal bodies to dissipate the heat. Alright. Now, grounding them, giving them a proper earthing is very, very important. If you run a VFD without earthing, if you touch the body of the VFD, you are going to get a severe shock. Alright. Okay. Then the cables that are powering the VFD and also the cable powering the motor must be shielded or screened. Okay, in India we don't particularly use screen power cables, but we use armored cables, which are very good. They are as good as screen cables. But only condition is that the armored cable should use proper metal glands which must be correctly grounded without compromise. Okay, now when you get a VFD and want it to be installed inside a control panel or a MCC, you have to observe the clearances. They will say that you have to leave some 3 inches, 4 inches above and below the VFD. Sometimes they may say you need not give much side clearance, you can stack them side to side. Whatever it is, you have to see what the manufacturer wants, and especially where the it's VFD's cooling fans are located. Okay, now you see the diagram on the left. This shows installation guidance for Yaskawa VFD. It shows that 2 inches must be left from the top. B should be the from the sides. He wants 30 millimeter minimum, and from the on the top, he wants 200 mm, that about 8 inches. All right, and on the diagram on the left, which is for a Siemens VFD, he says that you cannot mount the VFDs below one another, and he even says that do not install them without a partition. This is because the partition or air barrier which is shown in the diagram, that is to guide the airflow of each drive separately. Okay, now the other important thing is to calculate the airflow required for cooling. See, we have to not only consider VFD, we have to consider other components within the compartment to which the cooling fan is fixed. You have to add the heat dissipation of all those components within the cubicle, and the formula for airflow is given by airflow in liter per second is equal to power loss in watts divided by delta T, which is the increase in temperature over the ambient. Okay, in the last slide, we discussed how to mount the VFDs and to calculate the dissipation, and also we came to a formula uh, which tells us how many liters per second are required for cooling the cabinets insides for a given increase in temperature outside the ambient temperature. Okay, usually this increase in ambient temperature should not be more than 6 or 8 degrees. Okay, it's never to be allowed to cross some 50 odd degrees, never 60 degrees at all. Okay, so this shows now in the previous example, we let us say we had a total dissipation of 2045 watts. So we say that the airflow we required is about 141.58 lbs, and for a uh, delta T, suppose you take a cooling fan that is at airflow at 300 cubic feet per minute or 141.58 lbs. Now if we were to use this fan, then the corresponding increase in temperature would be 12.42 degrees. Now this is not a good idea. So we say we go for a higher rated cooling fan. Let's see what happens with airflow of 400 CFM, which gives you 188.78 liter per second. In this case, you see that the delta T now falls down to 9.31 degrees centigrade. This is the way you have to do it. Okay, now 9.31 is fine if the maximum ambient temperature is about 40 degrees, it will be alright. But if the ambient temperature maximum expected is 50 degrees, then you have to go for a higher capacity and see that the final temperature is well below 60 degrees. Fine. Okay, the VFD needs a circuit breaker upstream to protect it from short circuit. We have to look at the circuit breaker tripping curve to select it suitably. What we do is to see the time of tripping at about 1.5 multiples. Let's say that in this case we have at 1.5 times the rated current, that is on the x-axis of this graph. Okay, it will trip at slightly more than 50 seconds. That is actually the 1 minute line, 60 seconds. Alright, so this is very important for a short circuit because VFDs will draw surge currents from time to time, and especially at startup, then the capacitor will need to charge up. So we have to select it correctly. It is not necessary to select a circuit breaker to protect the VFD against overcurrent. No, the circuit breaker is for short circuit protection alone. Okay, the VFD itself is acceptable as a overcurrent protection device. Right? Okay. I once again say that protective earthing is extremely necessary. You should never power up a drive without it being proper earth. If the factory shed doesn't have an earthing connection, that is no excuse. I have seen factories like this. I have had them make earthing pits because we are using a drive. People are going to get a shock. All right. And the other thing is we have to use properly rated size of power cables, both that, which are coming to power the drive as well as to power the motor. Okay. Okay. Now, as I said earlier, the breaker selector should not trip at about 1 minute. It should trip. It should not trip for at least 1 minute at one and a half or two times the VFD's rated current. Now, the time between one and a half and two multiple is not all that significant because the we are well within the short circuit protection requirements. Okay, that short circuit currents are always much higher than one and a half or two. Now that one and a half to multiples is just to take care of starting surges. Now we come to parameterization. Many of these days drives have got fairly user-friendly LCD interfaces. Which will group the parameters in a very logical manner. The main things to set up, of course, are the motor nameplate details. Like, have the nameplate details around, take a picture of it on your mobile, and then go where the VFD's parameters for nameplate, or that is motor voltage rating, current rating, RPM, and all these things are mentioned. Look up the nameplate and enter the parameters. Okay, the correct do not accept the default values. Okay, the default values of rated current do not automatically follow the motor's kilowatt rating. Initially you'll get some value which is close, no, but for proper operation, you must go by the nameplate data. Okay. Then, above all, it is very important to set the maximum current and torque threshold. Okay. Now, these parameters that will be effective in overload protection, that is thermal equivalent of a thermal overload tripping. Okay, this is the exact same thing that prevents a motor from burning away. Okay, motors draw much heavier currents now and then. No, not on a sustained basis. Okay, so this has to be done according to the motor nameplate current. Fine. Okay, now we come to the parameterization of the I/O terminals of the VFD. Now, just like a PLC, I/Os, uh, VFD will have multiple inputs and output, digital inputs, digital outputs, analog input, analog outputs. Okay. Now, uh, we have to assign a certain functionality, like one DI input can be used for start stop, or one can be a emergency stop, one can be a momentary start, one input can be used for braking, one can be used for DC injection stop, things like that. So also the relay outputs are usually used for lighting up indicator lamps, such as for the trip condition, or to indicate green light saying that the motor is running. So you have to configure the relay outputs and wire these relay outputs into the control circuit of the panel. Okay. Now, of course, the VF pattern parameters are the other important thing. But basically, we have to you see that for example, you look at the digital inputs. You see, we have said that a typical input, can be used for a single start-stop command or a forward-reverse command. Okay, a group of three inputs, for example, DI 3, 4, 5, can be used in a combination of 3 bits. That each are every one of them is off to every one of them. 8 combinations of fixed speeds are possible. Okay, sometimes you can use them to decelerate or accelerate the drive speed. Okay, similarly, the relay outputs which are there, the digital there, the upper left uh, diagram for digital output shows 3 outputs. Each of these can be assigned to a certain function. One is to show that the drive is ready, or when it is running, or when there is a fault. These are potential free. They can be wired up to a external indicator lamp. Okay, or they can be even used to interlock other things, such as they can be used as inputs in PLC logic. Okay, this is the way. And on the right side, you have analog inputs and output. Sometimes, there are usually two analog inputs. The first analog input, you can it takes in 0 to 10 volts, and that 10 volts is also coming from within the VFD. Okay, so all you do is to connect a potentiometer as shown. No, you should connect a potentiometer that is higher than 1 kilo. No, don't connect a low value potentiometer. Don't connect 100 ohm, 500 ohm and all. No, no, it has to be higher than, it has to be typically about 5 kilo. Otherwise, that 10 volt supply will get overloaded. In the same way, you can use the analog outputs to represent something. Now, these analog outputs can be wired as analog inputs to a PLC system. Analog inputs can be had from a pressure transmitter or a level transmitter, and the drive can be used to you know respond to these things by configuring the drive to respond to these signals. Drives also have got built-in PID functions, which will maintain the pressure if these analog inputs are used for measuring the pressure. Got it? So, okay, as discussed in the previous slide, there are a number of functions that can be assigned to each input or output signal of the VFD. For example, the for digital inputs you can have values assigned such as on-off control, forward, reverse, speed change, position sensing, free wheel stop, DC injection braking, jogging. You can use them for logical interlocks and many things. Some 10-20 functions are easily had in any drive. These are typical thing. You would have seen the glass doors, sliding doors at many malls, airports, hospitals, and things like that. See, these are also driven by a small VFD. So you see that when the door is closing, they close rapidly, and just before they fully close, the speed is sensed, the position is sensed, and then they close very slowly so that the glass doors don't crash into each other, and that will be disastrous, isn't it? So likewise for digital outputs, we have got run stop indication, trip indication. There's a speed change event. There's a torque indication. Now this is important for cranes and things like that, because in cranes this digital output is used to release a brake. The brake must not be released till the time uh, the the VFD has developed enough torque. Okay, otherwise there will be a impulse loading on the hook of the train. But this kind of crane and winch application is a separate profession in itself. But just be aware that these features exist within drives. Okay, and there is also the possibility of combining all these parameters. Okay, then there are many other features like minimum maximum speeds. You can place boundaries. Then you can also give them acceleration, deceleration rates, means how fast it will accelerate, how slow it will decelerate, and things like that. And then for analog inputs, as I've said, you can use them for external speed reference. It can represent the process variable for PID control. You can use this as a external torque reference. You can use for temperature sensing, and all these are again fully configurable with all the other parameters. Okay, the parameters often refer between themselves. One parameter is used as a reference to another parameter, connected what Siemens called, you know, a binary connector, BICO, and all these things. Analog outputs can be used for a simple purpose like uh, for a digital panel, indicator. You can use that 4 to 20 milliampere output. You can show any parameter as 4 to 20 milliampere signal and display it on this one. This can also be used to drive let us say a control valve, uh, anything. It can be used as a reference for another drive. Okay, typically if nothing special is needed, they are used for just indicating the one output is used for indicating the speed, and another output is used for indicating the current. Of course, even these things are hardly needed because the uh, drive has got a LCD indicator which shows it. However, these 4 to 20 milliampere signals can be taken to a PLC's analog input, and that can be taken into the PLC logic. That is why all these things are given. Now, in this slide, we see how sliding doors are controlled with drives. There are limit switches that sense the door position and then control the speed. Okay. For pumps, you can configure pressure control, flow control using the PID functionality built within the VFD. Then, for elevators, elevators these days travel very fast. There are elevators which are traveling up to 4 meter per second. That's quite a speed, 4 meter per second. We don't realize it because it is smoothly accelerating and decelerating. Okay. Despite the speed, it has to slow down and slow down and stop exactly at the landing of any floor. We are traveling in the elevator, we don't realize this. But in the back end, it is the VFD that controls the speed, and there's a smooth acceleration and deceleration and a very accurate position sensing and things like that. Right? Okay, next, we take the example of hoists. As I told you, hoists such as these have got a brake. You know, the brake controls it engages the drum on which the wire rope is wound, so that the low under heavy loads the winch doesn't slip away. Okay, so these brakes are released not when the motor starts. They will be released when the drive has got enough torque, has developed enough torque. Okay. Now, for centrifuge, you need, these are very large inertia things. These are found in pharmaceutical plants, So you have to control the acceleration, deceleration times, That again depends on load and other things. So they take a long time to stop, and therefore you have to apply braking and all, or you can, control them through dynamic braking, through a resistor. You can even use regenerative braking. These are the features, where mechanical design is simplified by means of the features that are available with VFDs. Now, what are harmonics? See, harmonics are a multiple of the fundamental. That is, the drive, suppose it is rated at 50 hertz, 100 hertz, 150 hertz, 200 hertz, 250 hertz. These are the multiples or harmonics of the fundamental 50 hertz. Now, this is a kind of electrical pollution. That is a corruption of the quality of power that is delivered to motors, and this also travels upstream. That is, it causes interference in the power supply of the drive itself. Okay. Now, why is this happening? Is because the output of a VFD is not really a sinusoidal wave. It's not a smooth wave. It is a synthesized pulse width modulated, um, you know, sine wave, where the sine wave characteristics are modulated onto the switching frequency, and the as pulse width. What really happens is the inductions of the motor, the capacitance of the cables and things like that respond to the square wave impulses and create additional transients. These transients are not immediately apparent, but you can see them on an oscilloscope. Okay. Now, the damage caused them by them is also not apparent, but they will reduce the life of other electronic equipment and things like that, which are sharing the same power supply. However, there are standards to regulate these things so that this harmonics and all are well within acceptable limits. So the acceptable content of harmonics in the power supply to a drive and all, it is only about 3%. Some customers, they allow it to be 5%. Okay, but yes, they are there. If we have to take action, harmonics will be induced if the cable that is connecting to the VFD to its motor is very long. You get harmonics. You should be particularly careful if there are residential areas and all, and in the vicinity of the industry which is having a large number of high power drives and things like that. Okay. See, there are two kinds of harmonics actually. One is on the line side, that is on the line that is supplying power to the VFD. This is caused by the rectifier side. Now, because they are, arranged as a six-phase rectifier, the six rectifiers in a three-phase full wave configuration, they draw active power in six distinct pulses, and this has got the potential to push back reactive power, into the line that feeds. Okay, this is due to the reverberation on the supply feeder. If we don't take enough precaution, this harmonic distortion can be up to even 85%. And what the real nuisance is that this power, the polluted power supply that is available to other equipment, that will not be able to really use a sine wave, a smooth voltage. For example, if there are fluorescent tubes or electronic controllers, power electronic controllers, or communication equipment, these will have to withstand a fair amount of interference, which is why line filters are used. Okay, it's a affair involving some calculations, but we have to curb them. Okay, on the load side, as I explained earlier, the pulse width modulation synthesis, it is uh, basically a series of square waves, and this square wave, by its very nature, it is not a gradual rate of change of voltage. It is a very rapid change in voltage, and these voltages are at 415 volt and all are quite high, very high dV by dt. Actually, it is for three-phase 415 volt DC bus is switched on at about 530 volts or so. So this again uh, can stress the insulation of the motor. It will cause some kind of eddy currents, and the high frequency harmonics can even travel through the bearings of the motor. Okay, the resultant voltage is never zero, so always some current, it always passes through the motor body and shaft and things like that. Yeah, it is not readily apparent. It is bad in some cases where people don't use filters and all these things. Yeah, but ordinarily, if you take reasonable care, this is not such a problem. Okay, there are a few methods, common methods, such as line reactors. Line reactor is a filter, it's a choke that is put on the input side of the VFD. You see, it is a low cost thing. It can be used where the total harmonics can be third harmonics, that is usually the strongest one. That when it is up to, it can bring it down to about 30%. Then you can use a passive harmonic filter. And you can use a multi-pulse drive. Now this feature is a new feature which is increasingly available in many drives. So this multi-pulse drive is the more common variety, which is why the drive manufacturers themselves tell you that now we have brought down the harmonics to about 3%. Now they're saying it is 5%. Now multi-pulse drive means instead of a 6 pulse, they are using 12 pulse and 18 pulse designs, and then you have a active harmonic filter, which is again a built-in filter feature into some modern drives. Then you have got a active front end. What is an active and front end? This active front end, it interacts with the line itself. Now this is what manages the feeding back of active and reactive power back into the line, the supply line. So active front ends are commonly found in regenerative drives. Okay, this table lists out the different methods and the cost and things. But yes, these days the modern drives which are available, they are capable of intrinsically having a inherently low level harmonics. And if you add a little filter and output choke and things like that, output chokes are not really required if you have less than 50-meter cable distance to the motor. Okay, this is now this is only a brief summary. Now you have to go by the manufacturer recommendation and study to what extent is the drive itself is managing the harmonics. Okay, and very often people like Siemens, Yaskawa, Schneider, they say that this is the rating of the line filter, the choke. They give you some formula to calculate. So, but yes, this is how you mitigate the influence of harmonics. Okay, this table shows what can be done on the load side. Okay, typically, to prevent the harmonic induced eddy currents passing through the body of the motor, you can use a shaft grounding ring or brush. You know, then you know there's an amount of wear and tear involved with it. So it is in this case, it is better to use a motor that is having the ball bearing set in a way that is insulated from the motor body. Okay. Then there are this is what is called a common mode inductor choke. All right, this is also a low cost alternative, and there is also a load reactor. It can be a dV by dt filter. All these are different kinds of chokes. Okay, there's one of the better solutions is a sine wave filter. It's a little more expensive, but this has to be carefully selected. And there are not many manufacturers who are selling an economical product. Okay, then some people use a isolation transformer. Now this is not really needed for short cable lengths. However, in my experience, I have seen up to 50-meter cable length. You don't need to do anything special. A low cost, you know, output choke would do just fine. There are innumerable small manufacturers who will correctly calculate the what should be the inductance of that kind of choke, and then they work very well. So this is the practical side of things. Okay, we discussed IEEE 519 and how we must ensure that the total harmonic contents do not exceed what is allowed. Okay. Now, in a typical distribution transformer system, you have other loads which are also connected along with the VFD loads. And this table says how much can the harmonics be present in that system. Okay. So the first column shows the ratio of the short circuit current with respect to the total uh, loads at the point of connection. Okay, basically showing the multiple of 20 means the short circuit current uh, is 20 times the sum total of everything that is connected at the point of common connection. Basically, he is talking of what is in India we would call 5% impedance of the transformer winding. That is, the transformer voltage at no load and at full load, at no load would be higher than the full load secondary voltage by about 5%. It is this 5% that causes a 20 multiple increase in when the secondary is short circuited, because at that time the transformer's impedance is the only thing that limits the short circuit current. Okay, that calculation we'll handle in some other video. Okay, yes, but this 20 means it is nearly the entire load is 20% overload means 20 times short circuit current means, as I told you, it is 5% impedance or 5% drop in voltage between no load voltage and the full load voltage. Okay. And what does the second line mean? 20 to 50. See, when you say that the other loads at the point of common connection and the sum total of the VFD loads, your load between 20 and 50. So that means you are operating at about less than half the current of what was shown in the load one. That is why he is allowing a higher, what you call, harmonic content. So finally it boils down to the fraction of the transformer capacity that you're using. Okay, that means in all, what this fellow means to say is there is a it depends on the transformer. You have got a bigger transformer and smaller VFDs. How much do the VFDs plus the other loads at a point of common connection, uh, how much current do these take up with respect to the short circuit current of the transformer, right? So if you see 100 to 1000, it is a very small fraction really of transformer's capacity. So larger capacity transformer and the VFD loads do not amount to much. You can live with a higher amount of distortion. Okay, fine. Okay, friend, that would be all. I hope you have once again um, understood something useful that helps you in your work with configuring drives. This is the last in the series of this understanding VFDs. Please post your comments, your reviews, what do you think of my work in the comment section. I'll be only happy to improve my work in the line of your suggestions. See you later. Bye.